this part is BB or black box. Okay. You do not have any information about this process. Okay. These are mathematical relationships. If we simplify this thing and if we try to explain this particular process, we can say that this is somewhat nonlinear regression, highly complex nonlinear regression. In first process, that is response matrix, we have considered that process is linear. In this case, we are considering it to be nonlinear. Nonlinearity is there. So, this is your meta model or surrogate based approach. One is linear, another one is nonlinear. In embedding method, yeah, you can use linear programming to solve your problem and response matrix as constraint for that problem, because response matrix is your equality constraint. Okay. Equality, you have something in the left hand side, ultimate thing is there is relationship like this, Ax is equal to B. Okay. This is your input and this is your output, and this A matrix is your coefficient matrix. So, we multiply that coefficient matrix with the input to get the output. Okay. So, A x is equal to B, this is equality constraint. Also, this is called as binding constraint for your system, because you have to satisfy that constraint to satisfy the physical process. Okay. And to or to incorporate the physical process within your optimization process. Yeah, feasible region. You have to consider this thing. But in embedding method, we discretize the governing equation. So, if you have some partial differential equation or PDE, so you will get some discretized form, that is some equation which will be of the nature Ax is equal to B again. In this case, if your PDE is linear, then A matrix is your constant coefficients. A matrix is with constant coefficients, If PDE is nonlinear, A matrix is not constant. Okay. At every iteration this will change, and you have to satisfy the nonlinear relationship within your optimization algorithm. Okay. What is the advantage of this embedding technique? In embedding technique, you can discretize the whole domain using some numerical method or discretization method, I should say, like finite difference, or finite element, and we can use those equations within your optimization framework. the approach or concept is simple. Let us say that you have two equations, which is A is equal to 0, B is equal to 0. From your class 10 or 12 knowledge, you know that A square plus B square should have a minimum value, and that is A is equal to 0, B is equal to 0. So, if you solve this problem, so actually you are solving this thing. Okay. So, that is the basic concept for this embedding technique, that you can have linear or nonlinear equation for your system, but you can solve that one as constraints for your optimization model. Essentially, if your A matrix or coefficient matrix is linear, then you can solve the problem using linear programming technique. But another concept or point you should remember, that in any optimization algorithm or optimization formulation, there are two things. One is objective function, another one is constraint, okay, subject to some constraint. So, if your objective function is linear, constraint is linear, you can solution approach should be linear. Okay. If your objective is nonlinear, constraint is linear, then approach should be nonlinear. If your objective is linear, constraint is nonlinear, again your approach should be nonlinear programming. Okay. This should be clear. But in this case, another point you should remember, that your objective function should be differentiable. That is the primary requirement for using classical optimization techniques. Okay. Objective function should be differentiable let us say that I can solve the same problem, a square plus b square is equal to 0 as minimum of a modulus plus b modulus is equal to 0. Okay. But what is the problem? Differentiability is a problem for this modulus function. So, formulation is important for any optimization problem. So, you have to create your objective function such that you can solve it using a certain algorithm. Okay. Classical optimization, you can solve always differentiable functions. But if you have evolutionary algorithms like GA or genetic algorithm or simulated annealing or ant colony optimization or artificial immune systems or particle swarm optimization, these different techniques you can utilize with these kind of non-differentiable functions. Okay. But the problem is, in these evolutionary algorithms, your optima is not guaranteed. Okay. That should be clear. Optimum point is not guaranteed. You will get near optimum solution, but you cannot guarantee that there will be a optimum. But in classical optimization, you will get at least one local optima. There is I think Professor Datta has already discussed about local and global optima. So, at least you will get some local optima, but you cannot guarantee that thing in this evolutionary algorithms. But the advantage is that you will get a near optimal solution, and you can utilize your non-differentiable functions in the optimization framework. So, this is all about your embedding technique. Now, linked simulation. In linked simulation optimization, we have some optimization algorithm. And in this optimization algorithm, we consider this simulation model. So, what is the role of this simulation model in this optimization algorithm? So, if we closely look into this process, you will see that the use of this simulation model is for function evaluation. Either you have some input from the optimization model and you will get some output out of that. You will calculate the function. Now, why this function is required? If you have classical optimization, then you cannot directly utilize this function value. Why? In classical optimization, you need gradient of function. Okay, gradient of function. That means either you can calculate the gradient of f is a particular function, and x, let us say the variable, then for forward difference we can write it as f x plus delta x, and maybe y is there, it is a two variable function, then f x y divided by del x. So, from your simulation model, you have to calculate this one, you have to calculate this one, then only you can get the gradient value. Okay. So, gradient calculation is another computationally expensive process, okay, or computationally expensive step. So, what is the advantage of this soft computing techniques or your evolutionary algorithms, that is GASA? In that one, you do not need to calculate the gradient. You can directly utilize the function value to get your future population or future optimal values. In that one, we generally need to use some tournament selection, and tournament selections, your function values are directly utilized to get the ideal point or the better points. Okay. So, classical optimization, one disadvantage is that computationally expensive. Second one is your you need more number of function evaluations, and one advantage is there, that is or a disadvantage, that is you need differentiable functions. But evolutionary algorithms, the advantage is that you need direct evaluation of your function value. Second one, you can handle your this one your function candidate solutions easily, and you will get near global optimum solution, near global optimum. That is not exactly global optimal, but you will get near global optimal solution.
Exactly how the
linking works. Okay. Let us say that in optimization process, you need some inputs, some outputs. What should be the input for a flow problem? Let us say first problem is only flow problem. Let us say that we have one area and number of pumping wells are there, and we want to minimize the pumping and maximize the pumping, and hydraulic head should be within certain limits. Okay. That is a common problem. Now, maximization of total pumping, and subject to H should be more than H reference, that is for all points or all observation points, at least for observation points. This is your first objective, first constraint. Second constraint should be your binding constraint, that is your what should be your output? Output is H, which is a function of Q, In mathematical form, I have written it like this, but in this algorithm process, you have to input this H value or transfer this H value to the simulation model, and this Q value to this simulation model, and it will give you the H value for constraint calculation. That is, in optimization algorithm, we have input this discharge and output is this hydraulic head at all observation locations, and this Q value is for production well locations only. Okay, production well locations. So this is a simple optimization problem, but let us say that we have a flow and transport problem. Then you should have maximization of a discharge at production well and minimization of some maximum concentration, maximization of concentration at all observation locations for all observation locations, subject to we can link both hydraulic head, that is it should be greater than some reference, H is satisfied Q. At the same time, we also need G2 function which is related to Q, because from Q you will get H, from H you will get concentration. At the same time, your concentration is related to both hydraulic head and pumping valve. Okay. Any question with in this one? So transfer is clear, this transfer process.
So you are actually improving the Q and you are getting the corresponding hydraulic heads for the nodes.
Yeah. Okay. And that is flow and transport. If you want to handle in the same problem, then you have to incorporate both the constraints. Okay. And obviously, I have not written here. You should have binding your limit constraints. Limit constraint means there should be one lower limit and upper limit for each of the variables. You should not have a 0 and infinity value for your variables. Okay, decision variables. Now, to solve about the physical situation, let us say that what is the total capacity of your pump, that should be the limiting thing. Okay. So this much you can pump from your pump set. Okay. Below certain limit. Okay, that's why I have written H should be greater than some H reference. It should be greater than, not less than. Okay. Yeah. No, that is the capacity. You should not go below that level. Okay. So we have discussed two things. One is mathematical model and management model. Okay. Now, a mathematical model, or I should write it as physical model. Now, physical models can be of three types. Okay. One is analytical, second one is semi analytical, and third one is numerical. Okay. Analytical, I think you know that if you have analytical solution available for a particular differential equation, then it's easy that you give your input, you will get output out of that, and you can directly use that value for your link simulation optimization. Okay. That is easy. Semi analytical solution, that partly you incorporate numerical curves or something within analytical solution, and you get the solution out of that. We can call it as semi analytical solution. And numerical, it is completely your PD, you cannot solve using classical solving approaches. So, we need to discretize the governing equation and we need to solve that problem. Now, in this case you need boundary conditions. So, what are the types of boundary conditions? One is Dirichlet, second one is called as Neumann, and last one is called Robin. Okay. What is Dirichlet boundary condition? It is specified boundary condition. This is flux kind of boundary condition, and this is mixed kind of boundary condition. So, what is the use of this? Let us say you have a river, okay, and you know the stage value with time. So, to solve the groundwater flow model, you can directly specify the head and you can get the solution. Okay. That is your specified head boundary. Let us say that you have a pond in between and you are getting some constant flux or changing flux with time, or you have a boundary which is either zero flux, which is impermeable boundary. If you have mountainous or rocky strata, there will be no flow from that side. Okay. Obviously, flux should be 0, flux should be 0. So, that is called as zero Neumann boundary condition. If you have certain amount of flux available, then we will call it as normal flux boundary, or Robin kind of boundary condition, which is your mixed boundary condition. In that one, it is a combination of both, okay, both specified. So, recharge type of boundary conditions are your Robin kind of boundary condition. Now, to solve this mathematical model using this numerical approach, or by using this analytical or semi analytical approach, we need to consider the time domain. We have not talked about this time domain. So, let us say this is the starting point and this is the end point. So, you can have your management horizon, which is the total time between this 0 and this capital T. Okay. Now, in this case you can construct a model which is just equal to that time or less than that, okay, and you can calibrate this, and with available information in future you can update that model, and again you can extend this. So, this is a sequential process by which we generally solve the management problems. One is, this is your mathematical model. You know some initial condition here. With that initial condition and boundary condition, we can run this. Again, we will collect or monitoring at this point, and we will get certain amount of information. With that, we can update the model, and we can again utilize that model for the rest of the your management horizon or part of the management horizon. Again, we can go for your monitoring. But in this process, one thing you should remember, that in mathematical model you need to specify numerical time step. Okay. Numerical time step. Okay. Now, in this numerical time step, we divide the total time for mathematical model into different parts. Okay. So, essentially your management time step is not equal to your numerical time step. Okay. Management time step is not equal to your numerical time step. That should be clear. Now, this single objective and this multi objective optimization. So, in this one, in this single objective process, you already know that you can utilize classical approach or evolutionary approach. You will get single solution. Okay. But in this case, multiple solution. Let us say for a problem of saltwater intrusion, where we have maximization of pumping from production well and minimization of pumping from barrier wells, you will get some Pareto front, and you will get multiple solutions. Okay. Multiple solutions for this case. Now, in this case, you need secondary information. Secondary information to get the single solution. Okay. Ultimately, only one solution you can implement in the field. Okay. So, what is the use of this multiple objective optimization? That you can get multiple solutions, but based on the field situation, or technical feasibility, you can choose a particular solution and you can implement that in the field. So, you need secondary information for this process. Without secondary information, you cannot utilize the multi-objective optimization for your problem. So, secondary information is important. That can be any technical feasibility or economic viability that may be the thing you have to consider to get the single solution. Now, we'll talk about another important point. Let us use these terms: lumped, distributed, then deterministic, and stochastic. Okay. So, what is lumped and what is distributed, and what is this deterministic, stochastic? Any idea? Okay, unit. Okay, the single value can represent your whole system. Okay, and distributed means you will have multiple values. Okay, spatially varying values are available, and deterministic not time independent. Time independent is steady, unsteady. That thing is no uncertainty that is incorporated. Now, if we talk about this SS or specific storage, which is essentially a lumped distributed parameter. What is SS? SS or specific storage is related to confined aquifers. Okay. Confined aquifers, and that is related to the volume of water due to the unit change in the hydraulic head. Okay. So, in this case, lumped distributed things are utilized in the governing equation. Another parameter, that is K or hydraulic conductivity. In hydraulic conductivity, you can have different combinations. One is isotropic, homogeneous. Isotropic homogeneous means that if you consider two different locations within your domain, your values will not change either in direction or in space. Okay. Then you can have anisotropic homogeneous. Anisotropic homogeneous. Anisotropic means, let us say one direction you have kx, ky, and another location you will have kx, ky. That means spatially your values are not varying, but there is change in values if you change the direction. Okay. So, third combination can be isotropic heterogeneous and anisotropic heterogeneous. So, what is isotropic heterogeneous? That means K1 K2, but isotropic is K1 K1 both the directions. If you change space, K2 K2. And this is completely random, that is K1 K2 you can consider K3 K4, okay, anisotropic and heterogeneous. Now
actually I never understood this thing.
okay.
For the second one, the anisotropic and homogeneous, right? So this medium, how do you actually call it homogeneous? A homogeneous medium should have the same property everywhere inside.
Yeah, but isotropic nature, it's a vertically varying hydraulic conductivity. You will have horizontal hydraulic conductivity always greater than your vertical hydraulic conductivity. Homogeneous means related to medium property. Medium property, it's not directional. Material, you can see. Another one that is although stochastic concept utilized, that is homogeneous uniform. Let us say you have frequency distribution, and you have hydraulic conductivity value here, and you have a single value within your domain, then we call it as uniform and homogeneous. This is your deterministic concept, and we are talking about stochastic concept. Next is your uniform heterogeneous, another one can be non-uniform homogeneous, or non-uniform heterogeneous. So 4 combinations can be there. So in this case, you can have, let us say, 2 values within the domain, and 2 values are having mostly uniform, but you have 2 values within your domain, let us say K1 and K2. Okay. That means what is the thing you have? You have uniformity and non-uniformity, or homogeneous, heterogeneous. What kind of property is there? If I take this one, you have single value and all values are around that distribution. And third one, if you have bimodal distribution and you have 2 values so in stochastic concept we generally do not consider single value, or we consider that we have a value here k, and around that all values are distributed, and that is available in your aquifer system. Okay. So what is the best way of incorporating this stochastic concept in your model? That is called as random field generation. Random field generation. In random field generation, let us say we have one two-dimensional domain. We divide this into different grids. Let us say that within this aquifer system, I have taken reading at certain number of locations, maybe 1, 2, 3, 4 and 5 or 6. Okay. And from these observations, I can say that these values are not equal. Okay. These values are not equal. Now, I have to incorporate this information, that is 1, 2, 3, 4, 5 values within my groundwater model. So, how to do that? One concept is called as geostatistics. In geostatistics, sequential Gaussian simulation you can utilize to get different random fields based on the observed data. This will be Bayesian information for your system, that given these values you can generate random fields. So, this is, let us say, one random field, there will be another random field for your domain, let us say this is number 2. Like that, there will be n-th number of random fields. And how to utilize these things in your groundwater modeling? So, first we can start your groundwater model with one particular I is equal to 1 or first random field, okay, and we get some desired information which is H, okay, hydraulic head. Now, we will add or will utilize this second random field in the model and we will remove this I1, okay. We will get H value for second realization at same point, okay. So, from this one you can get mean value and your SD or standard deviation value. So, if you add or utilize all random fields in your groundwater model, you will get n-th number of values, okay. So, one by one you add and calculate the mean value and standard deviation value. Let us say that initially you have added or utilized 100 random fields to get the mean and standard deviation value. Then we can say that this is the mean and standard deviation value for 100 random fields. Okay. Now, we will start adding random fields one by one. Okay. So, if you add another random field, what is the change in the mean and standard deviation value? If it is negligible, so we can say that, so almost you have represented your field, and this mean value you can utilize for your simulation or optimization wherever you want to use. So, that is the concept that you can utilize for stochastic simulations, or to incorporate the uncertainty in hydraulic conductivity field. Okay.
Again, some kind of boundary condition.
In every process, there are certain assumptions. In this process, your consideration is that you know the boundary conditions, then only you are changing your parameter fields. Okay. So, at the same time, you cannot change all the parameters, and you cannot get a good result. Okay. Yeah. So, I think I will stop here, and next hour I will just try to conclude. Okay. Now, Professor Datta has already discussed about three things, that is, one is source identification, then saltwater intrusion and monitoring network design. Okay. So, why these problems are important, and we will try to look into the important points in this one. So, groundwater contamination, these are general statements. Groundwater contamination is a problem worldwide, often man-made. The source identification is a management necessity, and the most important thing is that what is the use of this source identification? Useful in fixing liabilities for pollution. Okay, that is the most important thing. Why this is required? Now, what is this? It is related to hydrogeology as forensic science. The source identification, ethics in this field, and safety of groundwater, that is required. This is migration of pollution. Basic problem is what? Basic problem is you have source strength, this is time. Let us say we have source 1, okay, and you have another source which is 2, and 1, 2, 3, 4, these are your monitoring locations. Now, one source is active for the second time period, and this particular source is active for 3 time periods, and there is gap of 1 time period. Okay. So, the forward modeling and whatever we call it as your simulation is forward modeling. Okay. In forward modeling, you know the strength and you can get the concentration or breakthrough curves. Okay. There will be combined effect of these two sources on the concentration that you will get from the monitoring wells. Now, in the inverse modeling, what is your approach? Your approach is that you know the concentration, your curve, breakthrough curve, and you have to find out what is this source strength, location, and other things. Okay. Now, the problem is most of the cases you may not get the actual breakthrough curve. Okay. Let us say that this is your T0 time and this is T1 time, okay, and this is your concentration. So, you have started your monitoring after this time T1. So, you will not get any information about this. So, this is called as TBC or truncated breakthrough curve. Okay. And source identification problems, this truncated breakthrough curve is the most common thing. Okay. So, whatever assumption you do, you have to be careful in that one, because TBC is the most common thing. Okay. So, what are the things you should know, or you have to find out? You have to find out what is the source location, what is the magnitude, and your period of activity. Source location, magnitude, and period of activity. So, inverse problem types. So, first inverse problem type is your backward problem. So, in this one, initial conditions are found. Okay. This is directly backward problem. Then coefficient inverse problem. This is the classical parameter estimation problem, where you know the response of the system, you try to find out what is the value of the parameter or parameters for a particular system. And last one, that is boundary inverse problem. You do not have or partial information about the boundary conditions. So, we try to get the boundary information value. Okay. So, you have to attack one particular problem, because you cannot solve all these problems in a single framework. Okay. Your objective should be clear, whether you are considering the backward problem or parameter estimation problem or coefficient inverse problem or boundary inverse problem. Okay. And source identification in water resources or environmental area, we generally solve that source identification problem as backward problem. Okay. We consider that you know the parameter values and you have information or correct information about the boundary conditions. Otherwise, you cannot solve that problem. Okay. This is clear. Now, difficulties in source identification. What are the difficulties? One is sparsely distributed observation wells. You already know that the sparsely distributed wells are available, and you may get this TBC or truncated breakthrough curve from those wells. Okay. You may not have complete information for your system, or partial information you have to proceed. Sparsity of observation data, that is your truncation breakthrough curve, inaccurate prediction of contaminant transport processes, and modeling errors, measurement errors. There can be measurement error, there can be modeling error associated with that. So, our assumption is that we know the boundary conditions, we know the parameter values. So, there can be modeling error associated with that. At the same time, when we are taking measurements from the field, there should be some amount of measurement error associated with that. There are billions possible combinations